Great. Yeah, good morning, everybody, and welcome to today's session. So, as I mentioned yesterday, what I'll do is I'll spend a little bit of time in the morning session today to sort of wind up uh, and summarize what we have talked about yesterday, and also talk about this. Actually, a couple of other uh, synthesis related topics that I could not get a chance to talk about yesterday. And then we will go into the hardware verification part, and of course, we will have some hands-on things also. So I just want to quickly recap what we talked about yesterday, and I was going through the notes that the notes from your day one, Sunil Simon's notes, and I realized that there was a bit of change of notation. So for the LTL, so I want to, I do not know whether that caused confusion yesterday, but I realized that he was using the circle symbol for the next operator. Next operator in Sunil Simon's lecture, and I have used the okay, so maybe I should write it next. So I have used X. So this is the next operator in the synthesis lecture, in Supratik's lecture. So that is one change. The next change I saw was here. Actually, I mean, both these notations are used. Unfortunately, we ended up using different notations. So this is the globally uh, operator, or always operator, in Sunil's lecture, and I have used G for this. So that perhaps was another confusion. And there was one more. So Sunil used the diamond operator for eventually, or finally, in Sunil's lecture. And I have used F for this. Okay, so I am not sure if this caused some confusion, but if it did, both of these notations are used. Uh, I have used X, G, and F. Sunil has used the circle, square, and diamond. But otherwise, they are the same. Their semantics is the same. The way you use them is the same. So this is one clarification I thought I should give from yesterday's lecture. If this caused any confusion, there was a slight change of notation from what Sunil used. But both of them are used in the literature. Both of them are sort of equally used. It's not that one is less used and one is more used. And there is, one more thing that I wanted to sort of say that yesterday, we looked at the following approach. We said that, okay, start from an LTL spec, And then from there, we went to a perhaps a non-deterministic uh, Buki automaton. And then from there, we went to a deterministic parity automaton. Right. And from there, we went to this parity game. And from there, we came up with a winning condition and yeah. So we came up with a winning condition, a winning strategy, basically winning region computation, which gave rise to the winning strategy, which basically told us whether the spec was realizable, realizability question answers the realizability uh, decision. And the second thing that it also told us is if it is realizable, then what is the winning strategy? And finally, from there, we of course saw how to construct a Mealy machine, right? So this was the kind of the steps used yesterday, and this is the classical way to do synthesis, in the sense that I mean the Strix tool does a bypass here and comes here, but after that things are the same. So this is a classical way to do synthesis, and very well studied, and you know uh, very well understood as well. And I think I mentioned this yesterday, that there is an exponential blow up here, there's an exponential blow up here. So we are already at a doubly exponential blow up, and after that, parity game. This is quasi polynomial time, and after that, the construction of the Mealy machine is, of course, it's polynomial time after that. So this is quasi polynomial. So this is, of course, completely polynomial, and this is quasi polynomial, and from there, this is polynomial. Okay, so the point is that while this is a very well studied and well understood flow, and indeed for a given LTL spec, we can answer all of these questions, whether it is realizable, and if it is realizable, we can come up with a realization. This has its limitations if there is a blow up over here, right? I mean, the worst case can blow up doubly exponentially, as I mentioned yesterday, 2 raised to 2 raised to n, where n is the size of the LTL spec. And if the blow up here can be contained, can be controlled, then of course the rest of it is very much practical. But sometimes the blow up here, for an arbitrary, I mean, we know that there are LTL formulas for which this blow up is inevitable. You cannot avoid this blow up. But at least for the kind of problems we looked at yesterday, it, at least the simple example we looked at, it didn't look like it blew up. And when we tried to do this implementations of other specifications using Strix, it was doing things fairly fast. So hopefully it was not blowing up too badly. So the question is that if we can control this blow up somehow, then I think the rest of it is fairly practical. So what are the ways in which we can control this blow up? I mean, yesterday we while using the Strix tool, we saw that the size of the implementation does vary based on maybe small changes that I introduced at the LTL spec. So the question is that, are there restrictions on the LTL spec that I can put so that this blow up is definitely controlled, so that after that things can be easily synthesized? Okay, so are there some restrictions on the LTL spec that we can put such that the whole thing becomes a little bit more tractable. And indeed, there is a very useful and very practical fragment of LTL that serves this purpose. So I wanted to talk about that a little bit because, this picture might say that, oh, this is really a hopeless situation. I mean, double exponential blow up is too bad. But as long as you can control this blow up, I'm going to show one well-studied fragment of LTL which allows you to control this blow up. You could have your own ways. I mean, just like yesterday, we saw that breaking up the formula into small parts, for each of which you know that there are nice deterministic automata. That also could be another way. So I'm going to now talk about one of the well-studied fragments of LTL that is used for synthesis, and this is called general reactivity of rank 1 specifications. Okay, so this is a fragment of LTL. So maybe I should write here. So this is a fragment of LTL. Okay, and how does this fragment look like? So formulas here are of this form, that you have a bunch of assumption formulas implying a bunch of guarantee formulas. Okay, and the number of guarantees can indeed be different from the number of assumptions. So I should say n over here. Okay, so you have a bunch of assumptions conjoined implying a bunch of guarantees conjoined, which basically means that if all of the assumptions are true, then each of the guarantees are going to be true. Now, there are restrictions on what you can use for either the assumption or the guarantee, and each of these assumption subformulas or guarantee subformulas is allowed to be one of these three types. So one are state formulas, which means you just talk about the atomic propositions, no temporal operators. So it's something like, using our example yesterday, where we had x1 and x2 as inputs and y1 and y2 as outputs. So you could say something like x1 or x1 implies y1, basically no temporal operators, just the atomic propositions and Boolean combinations of those. Or each of these could be a safety property, which is of the following type, that globally something holds, and this something could even have the following form, that if something holds now, then something should hold in the next step. I mean, this is actually, you can, if you put x implies x phi, phi implies x phi, then it is the same as saying globally phi. So this is not restricting what you could say earlier, but this is just saying that, in general, you could have it in this form. And liveness properties of the form, this very special form, GF phi. And if you, recall the semantics of G and F, this is saying that at all points of time, I should be able to see phi holding true sometime in the future. This basically means phi holds infinitely many times, because no matter where on the timeline you're standing, you can always see phi holding true in the future. So, if this has to happen at all points of time, then the only way this can happen is that phi must happen infinitely many times. So these are the three kind of restrictions that you have on the formulas AI and GJ. And if your individual formulas are of this type and your overall specification is of this type, then realizability can be solved in exponential time, which means that we have reduced we have taken off one exponent from what we had over here, and that is a big saving, right? I mean, 2 raised to n versus 2 raised to 2 raised to n is, for example, just to give you an idea, if n is 10, 2 raised to n is 1024, but 2 raised to 2 raised to n is 2 raised to 1024. Okay, that's a huge difference. So, using GR1 specs, being able to cut down the blow up to exponential is, I think, a huge savings in terms of real practical examples. But of course, it's still exponential. And really the exponential part comes from the safety properties. So if you don't have these safety properties, if you don't, if your specification can avoid these safety properties, or if your specification can use safety properties for which you know that there are nice, simple deterministic automata, then once again, you're actually in business. Then you can even avoid this exponential blow up. Okay. So let's see how each of these kinds of formulas are handled. And as I said, state formulas are, of course, fairly simple. There's really no blow up, and you're just keeping, whatever inputs are happening and whatever outputs you're generating, you're just keeping track of the Boolean values. Right? You don't need to remember anything beyond that. The safety formulas, as I just mentioned, so when you have this global thing, you need an exponential state space in general. And that's really because, at every state where phi is true, you need to remember what the next state should satisfy. And this business of remembering can really cause a blow up. There might be exponentially many things for you to remember in general. So this is the source of the exponential blow up. For the liveness formula, although it is of this type GF phi, there's a really nice, very nicely structured parity automaton with only 3 colors that can be used for this. And I'm just going to show you how this looks like. And so, what this means is that you don't really have any problems coming from here or from here. The problem really comes from here. And so somehow if you could tame this further down, in the sense that if you could either avoid safety formulas completely, or if you could, sort of talk about safety formulas for which there are small compact automata, deterministic automata, then once again you are in business. So I'm going to show you how this liveness thing translates to, and the rest of it is fairly standard. This, of course, doesn't require remembering anything, and this is a standard exponential state space blow. So here is how these GF properties translate to. Okay, so I'm just going to explain this diagram. So suppose, for the sake of simplicity, I'm just talking about GF of some assumption A1. Let us say this assumption A1 is completely a state formula. It's just Boolean combinations of atomic propositions. And I have M such assumptions, GF A1 to GF AM, where each of these AIs is just a Boolean combination of atomic propositions for the sake of simplicity. And similarly, I have GF G1 to Gn. These are the guarantees, right? So, this property is actually saying something quite non-trivial. If you think about it, what this property is saying is that GF, remember, means something happening infinitely often. So this is saying that if A1 happens infinitely often, if the assumption A1 becomes true infinitely often, and the assumption A2 becomes true infinitely often, and the assumption AN becomes true infinitely often, what this line that is shown up over here is, so this is saying that if A1 happens infinitely, assumption A1 becomes true infinitely often, until assumption AM becoming true infinitely often. So if each of these assumptions become true infinitely often, then each of the guarantees will also become true infinitely often. So this is, definitely talking about the temporal nature, the temporal relation between the assumptions and the guarantees. And, this is talking about things happening infinitely often. So it is not something that you can just look at a finite horizon and take care of. Right? So this is actually saying something, non-trivial, which can be useful for writing specifications of, real life systems, because this is actually saying something kind of interesting that if each of these assumptions happens infinitely often, each of these guarantees must happen infinitely often. Now, one could, of course, view this as an LTL formula, do a non-deterministic bouquet automaton, and then a deterministic parity automaton, and all of that. But there is a direct way to translate this to a deterministic parity automaton. So I'm just showing you what the deterministic parity automaton for this looks like. And it looks like this. This automaton has one outer loop, which is shown in this magenta color, which is traversed each time one of the guarantees becomes true. And within this outer loop, there are inner loops which are traversed, every time I have seen assumption A1 becoming true and assumption A2 becoming true and assumption AM becoming true. So each of these are M-length cycles, the inner loops corresponding to the M assumptions, and the outer loop is an N-length cycle. This should be N. The outer loop is an N-length cycle corresponding to the N guarantees. And the way this automaton operates is that it starts in the first inner loop, and in the first inner loop, it is going to traverse the first inner loop, trying to check whether A1 has happened and A2 has happened and AM has happened, right? So every time A1 has happened, and let us say G1 has not happened at all. I mean, this arrow with a G1 over here basically means that from any of these states, if you see a G1, you can directly come to the starting state of the next cycle over here. Right? So instead of drawing all of those arrows and making the diagram cluttered, I've shown it like this. So if from any of these states G1 appears, you immediately come to the starting state of the next inner cycle. So suppose G1 has not appeared, then what this is doing is it's making sure that it has seen A1 once, it has seen A2 once, and it has seen AM once. It has seen AM once. And then it's coming back again. If it has not seen G1 yet, it's again checking whether A1 is seen, A2 is seen, AM is seen, and so on. And of course, if A1 is not seen, then it cycles around here. If A2 is not seen, it cycles around here. If AM is not seen, it cycles around here. Right? So if you think about it, if let us say the assumption A1 doesn't happen infinitely often, suppose it happens only finitely often, what is going to happen? So you're going to go around this cycle. If these assumptions A1, A2 till AM, suppose it's the case that not all of them happen infinitely often. Let's say some of them happen only finitely often. So what's going to happen is you're going to go around this cycle a few times. And after that, you'll get stuck because let us say, A3 doesn't appear after some finite number of times. So you can't take whatever the arrow corresponding to A3, you'll get stuck in the corresponding loop, which says negation A3 and negation G1, right? So if it is the case that not all the assumptions here happen infinitely often, then if you're moving around this loop, you're going to get stuck at one of these states, these intermediate states, and you just keep looping around that state, right? But if all of the assumptions, and that is true for each one of these, because the way they depend on the assumptions are the same in each one of these. But if all the assumptions actually happened infinitely often, then you will be moving around this, right? And of course, the moment the G1 happens, you come here and then you start moving around this, and the moment G2 happens, you come here moving around this, and so on. So suppose it is indeed the case that all the assumptions happen infinitely often, and all the guarantees also happen infinitely often. Basically, the specification is satisfied. So then what you'll be doing is that you'll move around the first inner loop for some time, and then when the first guarantee comes, you'll move around this loop for some time. And then when this comes, you'll move around this for some time, right? And finally, you'll reach here, and again, you'll go back and keep doing this. So effectively, you'll be hitting this state infinitely often, right? This state is really saying, I have checked that each one of A1, A2 till AM happened, and then G1 happened, and then each one of A1, A2, AM happened, G2 happened, and so on and so forth, right? Is that clear? So, uh, yeah, yeah. So I think if I've drawn this correctly. Yeah, I think there is a slight problem. So, no, I think it's fine. This is fine. This is fine, right? So essentially, if everything is happening, as planned, which means that if the assumptions are happening infinitely often and the guarantees are happening infinitely often, you'll be hitting this state infinitely often. Even if the assumptions don't happen infinitely often, but all the guarantees are happening infinitely often, you will still be hitting this state infinitely often, right? Because as I said, from each of these states, when you see G1 happening, you come here and, so maybe none of the assumptions are happening, but just the guarantees are happening. So you'll be moving from here to here to here and again coming back here. But that is fine. The implication is indeed satisfied. If the right hand side evaluates to true, then you don't care where the left hand side evaluates to true or not. Right? The only way that this implication will not be satisfied is if the left hand side is true, but the right hand side is not true. Okay. Now, if the left hand side is true, but the right hand side is not true, then what is going to happen is that uh, uh, you are going to get stuck in one of these. The left hand side is not true means at least one assumption is not happening infinitely often, right? Sorry. We are talking about the left hand side being true, but the right hand side being not true, right? So if the left hand side is true, then these are indeed going around, but the right hand side is not true, which means that you can't, after some time, you kind of get stuck in one of these loops. You're not able to see one of the grants coming infinitely often, right? So, so what? So, what can we say in such a situation that the left hand side is true, but the right hand side is not true? What we can say is that we will be stuck in one of these loops because the left hand side is true. We will keep proceeding along this, but because the right hand side is not true, there is one grant that is not coming infinitely often. So after all the finite occurrences of the grant have happened, you will basically get stuck in the corresponding loop here, waiting for that grant, which is not going to come any further. So if you think about the run of this automaton, the infinite run of this automaton, you will see that the infinite run will get stuck in one of these loops, right? And if it gets stuck in one of these loops, it will be visiting this state infinitely often. Okay, I mean the corresponding state here infinitely often. So here, what I have done is, yeah, maybe I should do it the other way. Yeah. So let me just uh, make this as 0. This is the color in the parity automaton. I have indicated the color, and let me just make these as 2. Okay. So suppose these are colored with the color 2, and these are colored These are colored with the color 1 and this is colored with the color 0. So if everything is fine, if the grants are coming in infinitely often, then you're passing through this state infinitely often, and so the smallest color that you'll see repeating infinitely often will be 0, and that is even, and that's fine. The system wins. And that's an accepting run. If any one of these assumptions doesn't happen infinitely often, then the left hand side of this implication is false, in which case once again the specification holds. But then if one of the assumptions doesn't come infinitely often, then you'll basically be stuck in one of these loops. And so then the color that will show infinitely often will be 2, which is once again even. There will be only one color that will show infinitely often, which is 2, and so that is even, so that is also fine. You have an accepting run. But in the case where these are happening infinitely often, but these are not happening infinitely often, as we just discussed, you'll get stuck in one of these loops. You'll be moving around one of these loops forever. And if you're moving around one of these loops forever, then the smallest color that you see infinitely often is 1, which is odd. And that's the case where the run will not be accepted. Right? So this just shows that what the accepting runs of this parity automaton are the runs for which the smallest color that shows up is even. And those are exactly the runs where either one of the assumptions doesn't show up infinitely often, in which case the smallest color will be 2. But then if one of the assumptions doesn't show up infinitely often, this implication is already satisfied because the left-hand side of the implication is false. Or if all of the guarantees show up infinitely often, in which case the smallest color will be 0, that's also even, that's fine. And the only way that this automaton will reject an infinite sequence of states is if the smallest color that shows up infinitely often is 1, which means you're not able to reach this place infinitely often, reach the state infinitely often, which means you're really stuck over here. And when are you stuck over here? When you're not seeing one of the guarantees infinitely often. Right? After some point, you don't see this guarantee anymore. So that's exactly the situation where this is satisfied, but this is not satisfied, and the specification is violated. Now, is this a deterministic automaton? I mean, as you can see that the moves are completely deterministic. From a state, you know exactly when to move in, when to move to the next state, when to loop back, when to go to the next inner cycle, and so on. So this is a completely deterministic automaton. It's a parity automaton. We have made sure that the parity conditions are such that if the smallest color appearing infinitely often is even, then the corresponding run satisfies this formula. And if the smallest color that appears infinitely often is odd, then this run violates the formula. So this is a deterministic parity automaton. And look at the size of this automaton. I mean, if you had, right, m things here and n things here, the size of this is m times n, right? You have n copies of these, O of n times n. Some constants might be there. And that's really good. I mean, there is, instead of the double exponential, which could have happened if you had gone from here to a non-deterministic bookie and then to a deterministic parity, I have directly obtained a deterministic parity, which is actually linear in the size of the assumptions, in the number of assumptions, and in the number of guarantees. And that's the advantage of having special structured specifications, of restricting the specifications to be certain fragments for which you know that you can construct deterministic parity automaton using only few colors, using only few states. And if you have this, then you're in business. Basically, you have your deterministic parity automaton. After that, this just needs to be converted to a game, and you can run your the winning region calculation that I showed yesterday on that game, and you can get your both realizability questions answered, and if it is realizable, you can also get a winning strategy. So is this clear? Maybe I'd like to hear from some of the participants. Okay. Yeah. So, Bhaskar, Vyas, are you there? Bhaskar? Bhaskar, Vyas? Okay, not there. Gaurav? Gaurav Thakkar? Thakkar?
Yes,
Anyone?
sir.
Yeah. So was this clear what I just talked about?
Yes, yes. So, but I have one doubt. Like,
Yeah.
these grants, like, how do we decide on them? Because
How do no? These are part of the specification, right? So, for example, yesterday we looked at this text, uh, this. Okay, I don't have yesterday's slides here, but remember yesterday we looked at a specification which looks at like x1 implies fy1.
yes,
So, I mean, these G1 to Gn are guarantees; they are not grants.
okay,
So this could be a formula on x1 and y1.
okay. So it will be part of a specification.
Yeah, yeah. This is part
Yeah.
of the specification.
Okay.
This whole thing is part of the specification. So that's what I said, right? That uh, instead of having a general LTL specification, I'm talking about specification in a restricted fragment of LTL. And what is the restriction? That I have to write it in this form, that there are a bunch of assumptions implying a bunch of guarantees. And each of these assumptions and guarantees can be formulas in, of this type. Uh, and I'm now looking at this kind of formulas.
Okay. Like
Each
we
of
are
the,
not checking for liveness.
pardon me,
We are not checking for liveness properties in this
we are
case.
checking for liveness property.
Okay.
Okay, so let's
Okay.
go
Okay.
through this. So I'm looking at specifications. So we are talking about specifications,
Yes.
not in the full-blown LTL like what we saw yesterday, because the full-blown LTL has a worst-case
Exponential.
complexity which is really bad. 2 raised to 1024 is quite bad.
Yes.
Okay, so we are saying, can we restrict the logic in which we write the specification? Can we use a fragment of LTL as opposed to the whole LTL such that we have some control on how big this can be,
Okay.
right? And so this fragment of LTL that we are talking about is called general reactivity of rank 1 or GR1. And what is this fragment of LTL? What does it disallow me from using? What does it allow me to use? So this fragment of LTL, every formula must be of this type. A
Okay.
bunch of assumptions implies a bunch of formulas representing assumptions implies a bunch of formulas representing guarantees.
Guarantees.
Each of these formulas representing assumptions can be one of these types. Just only talking about atomic propositions, no temporal operators. Each of these can be of this type, which is talking about something that should hold globally,
Yes.
and or each of these could be one of this type, which is a Leibniz condition,
Yes.
right?
Okay.
Basically saying something should happen infinitely often. And what I just showed you is an instance of this where each of the AIs and the GJs are of this type. So
Okay.
that's what I've shown you here. Each of the AIs and the GJs are of the form a Leibniz property.
Okay. Okay.
Is that clear?
Yes. Yes.
Okay. So I'm basically showing you uh, a specification that has this template, that fits this template, in which each of these assumptions is of this form and each of these guarantees is also of this form, right? So that is what I'm talking about. And we saw yesterday that the whole problem was translating LTL spec to a deterministic parity automaton. This is the bottleneck step. After that, everything can be done. Okay, I mean, of course, this can also be done, but this leads to this huge blow up. So we are trying to restrict what kind of LTL to use, what fragment of LTL to use, so that we can avoid this huge blow up. And this is one such very well studied fragment of LTL, which avoids one exponent. And that's a big deal. I mean, avoiding one exponent is like going from 2 raised to 1024 to 1024. That's really a big deal. Okay. So while exponent is bad enough, I mean, double exponent is horrible, right? So we have gone from horrible to bad.
Yes.
So, right?
Yeah.
And what I was showing you is that why does writing a specification in this form give advantages when we are trying to convert it to a deterministic parity automaton? So state formulas in any case, you don't need an automaton to
Yes.
sort of represent state formulas. For the safety property, as I said, you will need an exponential blow up in any case, and that's the place where the exponential blow up comes from. But for the liveness part, which also appears like, an LTL formula and therefore possibly involves a blow up when we try to convert it to deterministic parity automaton, because of the specific structure of this GR1 specs involving liveness properties, it turns out that you don't get a blow up. In fact, you get something very, very compact. Right? Because the moment you write your GR1 formula, GR1 spec using liveness formulas for each of the assumptions and for each of the guarantees, you can actually construct this automaton syntactically. Right? You can just look at this formula and just construct this automaton. And this automaton, we have just seen that it's a deterministic automaton. It's a parity automaton in the sense that whatever runs here, whatever infinite runs of this automaton have the smallest color appearing infinitely often as even. They will correspond exactly to the sequences for which this formula is satisfied. And whatever runs of this automaton have the smallest color appearing infinitely often as odd. They will correspond exactly to the sequences of this automaton, to the sequences that violate this formula. So the sequences accepted by this parity automaton. How does a parity automaton accept a sequence? You look at the sequence of colors appearing infinitely often and we find the smallest color appearing infinitely often. If that is even, we say it is accepted. If that is odd, we say it is not accepted. Right? So the sequence of states accepted by the sequence of inputs accepted by this parity automaton are exactly the sequence of states for which this formula evaluates true, for which the spec evaluates to true. Right? And these A1 till AM could be your state-based formulas, for example. So they could be individual atomic propositions or they could be some Boolean combination of atomic propositions. Is that clear?
Yes, thank you.
Yeah. Okay, so this is actually fairly well studied in the literature, and this is what was used. In fact, I think this was the turning point when synthesis, reactive synthesis, the reactive synthesis problem has been studied by theoreticians for a very, very long time. But I think GR1, identification of GR1 was the first time when this was put to practical use. In fact, the entire AMBA AHB protocol was modeled using GR1. So you see that this is not such a, it's not such a restrictive fragment of LTL that you can't do useful things with it. I mean, the whole of AMBA AHB protocol could be modeled using this. And therefore, one could synthesize. And I think that was the first time when it became clear that this is really a useful thing. And I think subsequently, this has been used in a lot of robotics applications and other kinds of controller synthesis and all of that. So GR1 is quite useful in that sense. And this is one of the ways in which you tackle this complexity, this doubly exponential horrible complexity over here. One of the ways you tackle is you restrict the fragment of LTL so that you know for sure that this blow up cannot happen. Okay. So, what we covered yesterday was talking about the theory. I mean, it's important to understand the theory, what's going on behind, how do you start from an LTL spec and come up with a machine. But there are hurdles along the way. and there are fundamental hurdles. In fact, this bound cannot be avoided in general if you allow full-blown LTL specs. But then for practical synthesis purposes, do we need the whole of LTL? And perhaps not. But then is there a fragment of LTL that allows us or that guarantees us that this blow-up doesn't happen? And GR1 is one such fragment. One such fragment that has actually been used to do fairly non-trivial stuff. Okay,
Yeah.
so if you're trying to use automated synthesis tools for your own synthesis problem, first try to check if you can use GR1. If you can use GR1, or if you can, maybe tweak your spec a little bit so that it fits inside GR1, you're really in business.
Supratik, I have one question.
Yeah.
So, like, if there are safety properties sitting here, how does that get incorporated? Can we still use this clever construction?
No. I mean, if there is a safety property sitting where inside these things.
Yeah, because we're allowed to have safety properties also, right? So maybe even in assumption or in a guarantee.
Yeah. No. All I'm saying is that there are these three components of these formulas, right?
Right.
And the moment you have this, you are likely to incur an exponential state.
Yeah, that's fine. But can we still use this construction somehow, or do we have to really get down to the whole business of constructing a non-deterministic Yuki automata, parity automata? Is there still a syntactic way of handling that, or no?
Of handling safety?
Yeah, I mean, if we have a safety, we have a similar structure, and one of them is safety. Let's say the last guarantee is a safety property.
No, but I mean, so remember what am I when I say G1, I mean a particular guarantee, right? So when I label this arrow by G1, I'll have to know that G1 has happened. Now, if knowing G1 has happened is itself going to involve an exponential blow up, then this is not going to be linear anymore, right? So typically the way these properties are expressed in GR1 is that you have such properties where each of these are state formulas, and you have such properties.
Maybe I'm not making myself clear. So what I'm trying to say is that we have a very nice syntactic way of constructing the deterministic finite automata if we only have state properties and Leibniz properties.
Correct. If you only have state properties and Leibniz properties, yes.
Right. Now the problem is this the safety properties.
Yeah.
Right. So now, like if there is maybe a conjunct sitting at the end of the guarantees list, which is a safety property, in that case, is there still a nice syntactic way of translation, or do we have to really get down to the whole business of converting things the way we discussed yesterday?
Is okay. So let me understand. So is there a nice syntactic way of okay? So what are we doing? We are basically saying that I'm able to construct a deterministic parity automaton out of this, and of course this is very trivial deterministic parity automaton. Now, constructing the deterministic parity automaton here may involve an exponential blow up.
Right.
Okay. And then if you want to combine all of these together, then of course this exponential blow up will affect the overall result. I mean, it depends on how this formula is interacting with these other formulas. I mean, maybe this is also talking about some output. This is also talking about some output.
Right, but all I was asking is that is there still a syntactic way of, let's say, the safety property part I handle syntactic, like maybe I translate the way we discussed yesterday. Is there still a way of conjoining the safety and Leibniz properties syntactically, or?
No. That's not syntactic.
Acha, I see. Okay.
That is the usual product automaton and all of that.
Acha, so that still has to be done there.
Yeah.
Okay, I see. Okay.
But I mean, the point is, the product automaton really becomes bad if any one of the individual components is
Sure.
bad.
That I understand. Sure. Okay. So I was just thinking that is there a shortcut still? I mean, which is a clever shortcut, which is possible.
Not really. I mean, this kind of formulas can easily blow up.
I see. Okay.
I mean, it depends on how much you're nesting things inside it.
Sure. No, blow up is
So
one part, but I was wondering, just even algorithmically, is there a like a shortcut to constructing it? Uh, but perhaps not.
not in general, no.
Okay,
Right? So safety properties will lead to an exponential state blow up
I
in
see. I see.
general. And then if you try to combine these two, I mean, the fact that this has blown up can lead to a blow up in the whole thing,
Right,
right?
right.
So
Okay.
typically, what you would want to do is you'd like to have safety properties, as you said, which are, even if they blow up, they are small. There are not too many things that are perhaps involved in them.
Right, right.
So even if they blow up, they're small, and therefore you can sort of deal with them individually, and then you can sort of form some kind of Boolean structure on top of it.
Sure, sure, sure. I see. I see. Okay.
Right?
Sure. Thanks for that.
Yeah. And I mean, if this thing, so typically, I mean, the at least kind of formulas that I have seen, uh, I mean, this part, I mean, the blow up that really comes is from this part, but even that blow up is not too bad that it sort of takes the whole thing out of our hands. Right? I mean, it's 2 raised to n is the worst case. So in practice, you may not reach 2 raised to n over here. Right? But here, order of mn is the worst case. Right? So in practice, you may not reach this, you may not hit this worst case, and in which case you're still doing fine. But if you do hit this worst case and this has already blown up, then of course this can also blow up. So in the worst case, this is exponential. I mean, this is not polynomial at all, or quasi-polynomial. The worst case, it is exponential. So one might ask, why throw in these safety properties at all? Why not just keep them out and have everything nice and simple? But then I guess you also want to have a fragment which is useful. I mean, where you can write your properties as much as possible. And and this is kind of in there. I mean, the important thing to note is that even with this kind of safety properties, you can avoid the doubly exponential thing, right? I mean, if these are not being combined with arbitrary liveness and all of that, you can avoid the doubly exponential thing. Okay? You can basically construct deterministic automata that satisfy these properties, where each of these formulas are just state formulas. They just involve atomic propositions. You can construct deterministic automata for these which are exponential.
Right. Sure. Sure. Thanks.
If you start nesting one inside the other and all, then of course you're gone. Right? So so those restrictions are there. That you basically, essentially what we are saying is, use the temporal operators in very careful ways. Right? And if we can do that, if our specification can be sort of massaged into using the temporal operators in these careful ways, so that everything inside them are sort of simple to deal with, simple to handle, then we're fine. Did that answer your question?
Yes. 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 Yeah. Thanks. Thanks.
Okay. All right. So this was one approach. Let's see how much time I've already used up 1 hour. Okay, maybe yeah. So let me talk about another approach, since today we are talking about making synthesis practical after having studied the theory yesterday. So let me talk about this second approach, which is also an extremely practical approach. And in fact, I mean, I'll just show you why this is so practical. Once again, this actually cuts down one of those exponentials. And this also makes use of the power of constraint solvers like SAT solvers or SMT solvers. And therefore, this is a very promising approach, because as these constraint solvers keep improving over time, this approach will also gain in strength. Okay, so what is this bounded synthesis approach? So here we are saying that here there are no restrictions on the specification language, right? You have the full LTL for giving your specification, but you are going to restrict something about the implementation, right? Earlier, what we saw was that we restricted something about the specification, but after that we let whatever implementation come out of it. We were we went the full distance trying to get the full implementation out of it. But here we are saying that we are not going to restrict the specification. So the specification can be a full-blown LTL specification, but we're going to restrict something in the implementation. And what? So this is some implementation parameter. For example, the number of states in the implementation, but this doesn't have to be the only thing that you're bounding. You can bound, for example, the number of transitions in your milli machine also. You can bound the number of whatever cycles in your milli machine. You can, so you're basically putting some bound on some of the implementation parameters, some of the parameters of the system that you're going to synthesize, in order to make the search space finite. Okay. Now, where is the search space coming? So, if you go and look at what we did yesterday, right? I mean, from this LTL spec, when we went down to this deterministic parity automaton and got this parity game, after that, this winning region computation was really trying to find out what are the states in this system, what are the states in this game graph, what are the vertices in this game graph from which one player can win or the other player can win. And it's kind of doing this search on that game graph, where that game graph has been derived from this deterministic parity automaton and is potentially very large. Okay. And so this search can be very, very large because it has to search on this entire game graph. Now, if I say that, and of course, after it has searched it out, basically after the winning region is calculated, every winning strategy, every implementation that could have satisfied the specification can be obtained from the winning region computation. So in some sense, it has captured the entire space of implementations, if at all the specification was realizable. Now we want to restrict this search because, I mean, this is like a big space to search, and we are really saying that we're going to come up with something from which I can get any implementation. Every possible implementation can be obtained from this. So instead of doing that, what we are doing here is we are saying, okay, let's restrict the space of implementations. Let's cut down on what are the implementations that we're going to consider as candidate implementations. And let's see whether there is some implementation within this restricted space of implementations that satisfies the LTL spec. Okay. Now, I mean, one thing is that the moment I do this, you can say, oh, I mean, this problem has now suddenly become quite simple because, if I say that, okay, you can only use 10 states, there are only so many milli machines that you can build with 10 states. And you can say, I'll just list down all of them one by one, and then I'll check if any one of them satisfies the specification. So it becomes a kind of a model checking problem or a verification problem, which we are going to study in the next part of today's lectures, right? So one naive way of sort of solving this problem with this bound on the implementation parameter is that you can just say that, okay, let's enumerate all implementations, within the bounds, within the parameter bounds. And for every such implementation, call it M, check if M satisfies phi. Okay? So this is also called the model checking problem. We are given an implementation, we are given a specification, and we are trying to check if the model satisfies the specification. And if the answer is yes, I've got my implementation. If the answer is no, I'll go and try out the next implementation. And if I've exhausted all possible implementations and still the answer is no, I'll say that, okay, no, it's not possible to implement the specification within this much bound. It may be possible to implement it with a higher bound, but not within this much bound. Right? So you see that, putting this restriction on the implementation, leaving the specification completely unrestricted, gives us a simple naive method to sort of check for implementations, right? Why could we have not done this earlier in the case of when there were no restrictions put on the implementation? Because we did not know. I mean, there was no bound put on the implementation parameters. So, I mean, how do we know how large an implementation we need? I mean, in fact, the implementation can be as large as the size of the deterministic parity automaton. It may have as large as many states as the deterministic parity automaton, and that's a very, very large number. We definitely don't want to try out. I mean, just think about this, right? I mean, this will be like ridiculously hopeless search. So sorry. So here we said, yeah. So suppose I have, the size of this LTL spec is 10, and then the size of the deterministic automaton is 2 raised to 1024. And now we are saying that, okay, search among all milli machines which have 2 raised to 1024 states, right? So the number of states is up to 2 raised to 1024, but now there can be all kinds of transitions between them. And so if you're trying to search for all milli machines with up to 2 raised to 1024 states, I mean, one might as well give up, right? So we don't want to do that. We want to put our bounds far, far, far smaller than what 2 raised to n is, and even far smaller than what 2 raised to n is. I mean, even 2 raised to n might be too large a bound, right? So, but then, I can't answer the question here without, I mean, this winning region computation happens on the parity game, which has the same size as the deterministic parity automaton. So I can't answer this question unless I have seen the full graph, full game graph, right? So therefore, the question that bounded synthesis is answering is something that makes sense only if this bound n is, small enough. I mean, if I'm willing to make the bound n as large as 2 raised to n, then of course, I can solve my original problem also, but of course, that doesn't make sense. Okay. So enumerating each one of them and checking this, I mean, this might be a naive approach. I mean, maybe even for, maybe I can say I want to look up to 50 states, but then, the total number of automata or the total number of milli machines implementations that you can build on 50 states is actually fairly large, right? I mean, so just to give you an idea of how large it can be, right? We are basically talking about, right? How to, let's say, build next state transition functions, right? So if I have 50 states, then I have to build this graph or the milli machine graph on the milli machine state transition graph on 50 states. And what does it mean? I have to figure out which state goes to which state on what condition, right? So if you think about it, we are talking about a table where if I say this is the current state and this is the input and this will be the output and that will be the next state, right? So, inputs, if there are, let us say, m inputs, m binary inputs, so there will be 2 raised to m possibilities of this. And now you have you have to put a current state. Let us say I put state S0 over here. And for each of these 2 raised to m possibilities of this input, I have to figure out what the next state should be, right? So if there are 50 states, there are 50 possibilities of in the first place corresponding to each of which there are 50 possibilities in the second place, there are 50 possibilities in the third place. So it is really 50 raised to 2 raised to m for just one state. Okay. And now I have to do this for each state. Right? I have to say, okay, now for S1 again, for each of the 2 raised to m inputs. So this will be 50 times this. And you can see that even for small values of m, this number is going to become astronomically large, right? I mean, even for m is, I don't know, maybe the number of inputs, right? So let us say number of inputs is, even if I say that is, let us say 2 or 3 number of inputs, so 50 raised to 8 is already very large. It is 5 raised to 8 into 10 raised to 8. Okay, so that's a very large number. So, and this is just for 3 inputs and 50 states, right? So explicitly listing out, and here I have not even considered, what kind of outputs can show up over here, right? If there are n outputs in each of these entries, you can put one of 2 raised to n values, right? So it is each one of these, will be coupled with one of 2 raised to n values for each one of these. So it's really, I mean, the numbers start growing very large if you are going to explicitly list them out. If you're going to explicitly consider all automata with 50 states, then the numbers really grow very large. So we don't want to do that. We want to do something smarter. Okay? And that's all that bounded synthesis is about. So we're going to limit the search space. Of course, the search space is now constrained. And we're going to use a constraint solver to either find a solution, right? A Mealy machine within 50 states that satisfies the specification, for example, or to show the absence of solutions within the given bounds. So this doesn't mean that the specification is unrealizable. It just means that there is no implementation. You cannot realize the specification within the given bound. If your constraint solver says, no, I cannot satisfy this. And in this case, you can iteratively increase the bound and try again. How far should you increase the bound? In principle, all the way up to 2 raised to 2 raised to n. But of course, that's impractical. So we just increase the bound up to, whatever limit we want. And then maybe after that, we say, okay, I mean, it looks like the state machine is going to be huge. And perhaps we need to go and do engineer the specification so that we can get smaller specification. Okay. So let's see how this works. So maybe, Shubhajit, what I'll do is I'll use the remaining time just to cover this, and we'll start on hardware verification after the break. Is that fine?
Yeah, sure, of course, yeah. Perfect.
Yeah. Okay. So let's see how this flow proceeds. So we start from an unconstrained LTL formula. And then instead of going through non-deterministic Boki automaton and then a deterministic parity automaton or directly a deterministic parity automaton, we build what is called a universal co-Boki automaton. And I'm just going to say what this is. The interesting part is it is okay for this automaton to be non-deterministic. We do not require that this has to be a deterministic automaton. Okay. So once again, there is an exponential blow up in the worst case over here. And in the size of the specification, okay, and we will see that I mean this does have a problem, right? I mean if this has already blown up, then even bounded synthesis is going to have problems. But at least the second exponent is avoided. So we have this universal Boki automaton, possibly an exponential blow up in the worst case, not always, but in the worst case. But then after we get this, we are not going to try to determinize it. We are not going to try to solve a game. We are just going to come up with a system of constraints which expresses how an implementation should relate to this universal co-Boki automaton. And then, the system of constraints is in general on natural numbers. So, in general, such constraints on natural numbers may be hard to solve. But then we bound the parameters. So we say, okay, these are the maximum natural numbers we're going to look at, bounded natural numbers. And that gives us a bounded set of constraints. And once we bound natural numbers, we can, of course, represent them as bit vectors, convert them to propositional formulas, bit vector formulas. and use the very powerful SAT SMT solvers that are out there to either get a solution, in which case we get a system implementation, or the constraint solver says no solution, then we know that there is no way of implementing the specification within the given bounds of the parameters. And then we can take a call on whether to increase the bounds or not. And if we want to increase the bounds, we again, so it's the same system of constraints, but we now try to solve it with perhaps increased bounds, improved bounds, and then this loop can continue. Okay, so this is the overall idea. So there are two key steps that we need to talk about over here. One is this one, right? Which is how do I go from an LTL formula to universal Kobuki automaton? The second is this one. How do I go from a universal Kobuki automaton to a system of constraints? And after that, putting a bound and solving it is, basically any SAT SMT solver. You can do it once you put a bound there. So let's talk about these two briefly. So first, let's talk about the LTL formula to universal Kobuki automaton. So what is a universal Kobuki automaton? So it is like a Buki automaton, except that there are these two things. One we say universal and the other we say Kobuki. So in a Buki automaton, let's say a non-deterministic Buki automaton, we are worried about whether there exists one run of the system that hits the final state infinitely often. So we are worried about this one run, right? In a universal Kobuki automaton, the universal means we're worried about all runs, okay? Not one run. So we're worried about all runs on an infinite world. And the Kobuki says that, in a Buki, we are required to visit a final state infinitely often. In the Kobuki, we say must visit the final state finitely often, not infinitely often. It's a complement of the Buki condition. That's why it's Kobuki. Okay. So a universal Kobuki automaton accepts an infinite world. In general, this is a non-deterministic automaton, so there can be multiple runs on an infinite world. So the automaton will accept an infinite world if every run of the automaton on the infinite world visits final states only finitely often. So the places where it gets stuck, or the places where it eventually starts, cycling around, the states where it eventually starts cycling around must all be non-final states. So, for this reason, the final states here in the Buki automaton, the final states were also called accepting states because, we visit them infinitely often and then the automaton accepts the language. Here, if these final states are visited infinitely often, even by one run, then the word is rejected. The infinite word is rejected. So therefore, we also call these final states as rejecting states rather than accepting states. Right? I mean, they are marked as final, but their job is to rejecting states. Right? So here I have tried to draw a universal Kobuki automaton for our favorite LTL specification that we were looking at. And let me just tell you why this is the universal Kobuki automaton for that formula. And then I'll tell you how to construct in general. It's actually not very difficult to construct in general. Okay. So what is this saying? This is our formula yesterday. So we know what this means. Let's not get into that now. But let's just look at what this automaton is doing. Okay. So this is its start state. This is the start state. And it always has a transition back to the start state, no matter what it sees, which means that the start state is always part of a run, right? No matter what word you give, you will always have the start state over there, right? So non-deterministically, I can always take this transition. So if I actually get a word, if I get a sequence of states which satisfies this specification, what does it mean? That in that, y1 and y2 never appear together. So this transition can never be taken, right? Because once this transition gets taken, after that you're stuck here. So then there is no way of accepting the run, right? You will have to reject the run because that thing which came here, that run which came here, will always be visiting this final state infinitely often. So, so basically, if it if it is not coming here, I'm looking at the words accepted by this automaton, so it cannot come here and get stuck, which means that it can never see y1 and y2. So that's what this is taken care of here. And what this says is that if it sees x1 at any point of time, then the non-deterministic automaton can branch off one run over here, the other run can continue wherever it was. But once it comes here, if it doesn't see a y1 ever again after that, then it will get stuck here. So if you have to avoid getting stuck here, you have to give a y1 so that this transition cannot be taken, and this is a non-deterministic automaton, which means the run will stop here. The run will not proceed here. The run will terminate here. It's the same as saying that you go to a sync state and then you just keep cycling around the sync state. Okay. And similarly, if you see an x2, you have to see a y2 sometime in the future, because otherwise you'll get stuck here. And it is perfectly possible that you have seen an x1, you have not seen a y1 so far, and then you have seen an x2. So this is the place where non-determinism comes in really useful, because if you've seen an x1, you don't want to be coming and waiting in this state for x2. Because our automaton is non-deterministic, so while one run can go here and wait for y1, the other run can continue over here. So that other run, when it sees x2, can come here. So now you have one run waiting here for y1, another run waiting here for y2, and the third run already moving around this, maybe waiting for another x1, maybe waiting for another x2, whatever, right? So the run that is coming and waiting here for y1, if that doesn't see a y1, it will get stuck here, and that will cause the word to be rejected because it's visiting a final state infinitely often. And the run that came here, it's a different run from the run that was waiting here for a y1. If it doesn't see a y2, it will get stuck here, and then it will get rejected, because then you'll have one run which is visiting a final state infinitely often. So in order to kill these runs that came here, you have to produce a y1 sometime in the future, and you have to produce a y2 sometime in the future, assuming x1 and x2 had been produced in the past. And so that's exactly what we want, right? So is this clear, at least at an intuitive level, that the runs that will cause this automaton to really, basically every run that reaches this state must eventually get killed, in the sense that it must eventually stop. There should be no way to proceed further. Every run that comes here must eventually stop, no way to proceed further. And of course, it should not come here, because if it comes here, then it gets stuck here, right? So all the runs that satisfy these three things are basically saying, if you see an x1, you have to see a y1 in the future. If you see an x2, you have to see a y2 in the future, and you should never see a y1 and y2 together. And that's exactly what this is saying. Okay, so this is a universal Kobuki automaton for this specification that we have been looking at since yesterday. And in general, given a temporal LTL LTL formula phi, how do I construct a universal Kobuki automaton? So one straightforward way to do this is to take the formula phi and write out a new formula, negation phi, and then construct a non-deterministic Buki automata for negation phi. Okay. So what will this non-deterministic Buki automata do for negation phi? It will make sure that every sequence that violates phi has at least one run that cycles around a final state infinitely often. Correct? Because that's the property of a non-deterministic Buki automaton, that every infinite sequence that is accepted by it will have at least one run which will go and cycle around a final state infinitely often. Right? Now, if the only things that we allow to cycle around final states infinitely often are those infinite runs that violate phi, then every run that satisfies phi will see these final states only finitely often. Correct? This NBA being, since I'm constructing this NBA from negation phi, the only runs that it allows to cycle around final states infinitely often are those that satisfy negation phi, and therefore those that violate phi, which means that every sequence that satisfies phi won't get to run around the final states infinitely often here, which means that all possible runs of this NBA on sequences that satisfy phi can only visit the final states finitely often. There won't be even one run among them which will visit a final state infinitely often, because if it did, that would have been accepted by this NBA and that would have satisfied negation phi and not phi. Okay, so the construction is really straightforward. Take the formula phi, put a negation before it. That's also an LTL formula. Use your standard LTL to NBA construction. Get the automaton, and then instead of viewing that automaton as a non-deterministic Bookey automaton, just view it as a universal co-Bookey automaton. The automaton is the same. We're just going to interpret the way runs are going to get accepted. Reinterpret the way runs are going to get accepted. Is that clear? Is this clear? I think this idea is important for understanding the bounded synthesis. Okay. Anybody? Himanshu?
Yes, sir.
Is it clear what a universal co-Bookey automaton is?
Yes, sir.
Okay. Krishna? Yeah, go ahead. Somebody has a question.
Hello, sir. Actually, I have a question regarding the NBA construction which you just said. Sir, is it the case that like any NBA can be thought of as a universal Kobuki automaton for some LTL specification? Like, I mean, for for some phi, if like if I could construct an NBA, then it is a universal Kobuki automaton.
For negation phi.
But
If for a certain, I mean, basically you're talking about this. So if for a certain phi you construct an NBA, then this NBA is the same as the universal Kobuki automaton
for negation phi.
for negation phi.
Okay. Thank you, sir.
Yeah, sure. Okay, great. So if you have understood this, then let's see. So now I'm going to take this. So I'm going to take my LTL formula, construct the universal Kobuki automaton, and I'm going to try to see how, I mean, under what conditions can I say, what are the system of constraints that I should have so that I can say an implementation really implements the specification that is represented by this universal Kobuki automaton, right? Our LTL spec phi that was there. From there, I obtained this universal Kobuki automaton. And now, suppose I give you an arbitrary implementation, which may or may not really implement the specification, right? And here I have taken this, that very naive implementation we were looking at yesterday, where it just keeps flipping y1 and y2 alternately, right? So first it sets y1 to true, y2 to false, and it sets y1 to false, y2 to true, and just keeps doing this. And actually, yesterday we saw that this was a correct implementation as far as the specification that we gave was concerned. In fact, Strix was also generating this, right? So, but I've just taken it here just for the sake of simplicity. You can take any arbitrary implementation. What we're going to do is we're planning to write down what it means for an implementation to satisfy the specification. So the first thing that we'll do is we will take the cross product of these two. Okay. So just to keep things simple, what I'll do is I'll basically copy this. Okay, I should copy this. So I'll just draw it out here. So there is this, and then there are these three reds. And so product, right? So each state here will be paired with each state here, and I'll have a copy of that. Here, And I will say that, okay, all of these states are really paired with, you know, so these, oh, sorry. Yeah. Okay. So all of these states are paired with the magenta state from here. This is the product, right? So I'm just representing the product like this. And all of these states here are paired with the orange state from there. Is this clear what I mean by this? I'm just, product will have a state from here and a state from here. So I'm just, maybe I just messed it up. Okay. Let me write it without the intersections. So this. So this whole thing is a state. It has a pair of states. And let's write this like this. Okay. So the product of these two things will have, in this case, 4 into 2, 8 states, look like this. And I will have transitions between them in the usual way, right? So for example, from here, right, since there is a self loop that comes back here, so I guess I will always have a transition which goes like this, right? Because I mean, from this, should say from this to this, because this blue can go to the blue on anything, and this magenta can go to the orange on a y1 and negation y2. Okay, and then I can say that, okay, even now this can come back here, of course, on y2 and negation y1, a similar token, correct? And then suppose an x1 comes, so this blue will go to this red, and where should we go here on an x1? We don't go anywhere, we just stay here only, right? So if just an x1 has come and the other things have not come, so we just go from here to here. Once again, from this combination of states to this combination of states on an x1. And then if negation y1 comes, then I will of course go here, right? But so the point is this, that can I come back? Okay, so I'm in this pink state, right? And from the pink state, if a negation y1 comes, where do I go? I don't have anywhere to go, right? Because from the pink state, I don't have an output labeled negation y1, correct? But if I was here, let us say that I came here, right? Blue to the first marked red on an x1, and I've gone from the magenta to the orange here, and now a negation y1 came, so then I can go back to the magenta, but this negation y1 will keep me over here. So you see that this will now come back here. Is this clear? I'm really drawing the product construction. It's the standard product construction. So from the blue on an x1, I can definitely come to this red, but and from the magenta on an x1, I can come to this red. But from here on a negation y1, I have nowhere to go, because from the magenta there is no output label negation y1. And of course, this should be x1. Yeah, so this should be x1 and x1 and y1 and negation y2, right? So to come from here to here, I have x1, and presumably there are no y1s, no y2s, So I'm just staying over here, the magenta state. But once I come here, even if I get a negation y1, I have nowhere to move, because from here on a negation y1, I have nowhere to move. I mean, basically, there's only one thing going out of it, which goes here. Okay. And similarly, from here, if I had x1 and y1 and negation y2, the x1 would have brought me from the blue to the red final state, rejecting state, and the y1 and negation y2 would have brought me to the orange state. And if I'm in the orange state, and then if I see negation y1, y2 and negation y1 rather, then from the orange state I can go to the magenta state, and from this state I can cycle back to its own self, right? Remember, these two are basically copies of this. So because I've seen a negation y1, so I can cycle back. Okay. So I'm going to draw this product automaton from any given automata that any implementation that you give me. I'll just take the cross product of this and draw this automaton. Now, there is one interesting property of this product automaton, is that you can think of this guy as telling what kind of sequences will come out of the system, right? This is really the Milli machine of the system. So this is telling what kind of sequences are going to come out of the system. And this guy is really checking whether the sequences are acceptable or not. And how is it checking? If it finds the sequence that is coming out of the system, there is one run of it which goes and cycles around a rejecting state infinitely often, then of course that implementation is wrong, because this implementation is generating a sequence which, when I feed here, it has a run which is cycling around a rejecting state infinitely often. So that sequence violates the specification, but the implementation is generating that sequence, so the implementation is not satisfying that specification. On the other hand, if every sequence that can come out of the implementation is such that it cannot cycle around these rejecting states infinitely often, then we know that every sequence coming out of the specification satisfies the coming out of this implementation satisfies the specification, and therefore this is a correct implementation. So how do we keep track of how many times we have visited a rejecting state as this product machine is working, right? This is a product machine. The implementation part of it, which is the magenta and orange, it is telling you what sequences can be generated. The universal Kobuki automaton, which comes from the spec, that is trying to check whether you are hitting whether the sequence that is generated by the implementation is hitting a final state, is hitting a rejecting state infinitely often. So what we want to do is, we want to come up with numbers on each of these states that tell us whether how many times can I reach this state. Okay. I mean, what is the maximum number of times that I can reach this state? So here, with this little, I didn't want to draw out the whole thing here because it looks very cluttered. But here, if you look at this little fragment that we have drawn out, what do you see? Maybe our starting state is here because this was the starting state here and that was the starting state there. And what you see is that I can be cycling around this for quite some time. Okay. And then maybe I come here and I hit a rejecting state, but then there's no way to go out of there. Or I come here, I hit a rejecting state, and from there I can go here, but then there's no way to go out from there. Okay. So all I need to check is, in this product automaton, is there a way to go from a rejecting state back to itself? Okay. So you can think of it like, checking for the existence of a cycle from the rejecting states back to itself. Okay. And of course, the way this is the way this can be set up as a constraint system is you can say that, okay, how many times have I seen a rejecting state, or how many times have I visited a rejecting state when I am in one of these states? So for example, when I'm here, that number is 0, right? What should I use? Blue. Yeah. So when I'm in this state, how many times have I visited a rejecting state? It's 0. If I go here, it's still 0, right? I'm talking about visiting a rejecting state in this product automaton or in this product structure. So here it is 0, here it is 0. And of course, since it is 0, I come here, there is no rejecting state, it continues to stay at 0. Come here, no rejecting state, continues to stay at 0, and so on. Now, if I come here, from 0, I'm coming here. So I can say, well, because from 0, I'm coming here, so I have seen this 0 plus 1 times. So it is, once. From here, if I come here, I say, okay, it is 0 plus 1 times, it is 1. But from 1 also I can come here. So it is 1 plus 1 2 times. And so this 1 gets superseded by 2. Right? But after that, I don't have a way to move out from here. Right? And what I've drawn here for this state A, a similar situation is going to happen for the state C. Right? I mean, they're kind of symmetric. Now, what happens for the state B? So from here, when can I reach here? When both Y1 and Y2 are generated. Right? So starting from this state, if both Y1 and Y2 are generated, can I reach here? I can't, because from here, there is no outgoing transition on Y1 and Y2. It's not that it loops back here on Y1 and Y2. From here, can I reach here if both Y1 and Y2 are generated? I can't, because from the orange state, there is no outgoing transition on Y1 and Y2. So therefore, these two states, the middle state, which is another state that can cause an infinite number of visits, these are actually unreachable. I can't even reach these states in this product automaton, because from this magenta and orange state, there is no Y1 and Y2. So, I mean, how am I going to even reach here? To reach here, I need Y1 and Y2. Okay. And for the other part, it's the same. I mean, what I did for X1, it will be a similar thing for X2 over here. So you can very well see that in this product automaton that I have, constructed here partly, if we just try to put a number on each of the states, saying that how many times can I reach that, how many times have I seen a rejecting state when in a run I arrive at this state. So suppose in a run I arrive at this state, what is the maximum number of times I could have seen a rejecting state? So here it is 0, here it is 0, here it is 1, here it could have been 1, it could have been 2. So the maximum number of times I could have seen the rejecting state is 2. And this is the number that we are going to calculate as a system of constraints. Right? So what we will do is, we will draw this product automaton and we will say, okay, there's a number associated, there's a natural number that is associated with each state over here. And I have this constraint that whenever I have a transition, the natural number here has to be greater. Whenever I have a transition to a rejecting state, the state I'm reaching has a rejecting component in it, then the number here has to be greater than the number here. It's not necessarily the number here plus 1 as we just saw here, because there might be another path which makes it larger. But the number here has to be greater than the number here. The number here has to be greater than the number here. Whenever I'm reaching a rejecting state, the number here has to be greater than the number here. But if I'm reaching a non-rejecting state, then the number here has to be either greater than or equal to the number here. Because maybe the number here is already higher, right? I mean, maybe the number here was already 3. Now, when I come here, if I've already seen 3 here, then at most 3, which means basically there is a run that makes me see rejecting states thrice when I reach here. So when I come here, I will also see it thrice. But maybe there was another state where I had seen it once. So when I reach here, it will be once. So now, what happens is that I have to take the maximum of that 1 and 3. And it's basically the same thing here. Here I did 0 plus 1, 1 plus 1, and took the maximum. if I'm coming to a state that is not a rejecting state, then I'll look at the number from here, and that same number should show up here, but maybe there is already a higher number already over there. So then I have to take the max of those two, right? So whenever I'm coming to a non-rejecting state, the number here is greater than equal to the number here. And whenever I'm coming to a rejecting state, the number here is strictly greater than the number here. Okay. And that is it. I mean, you basically get a set of constraints on natural numbers, on integers. If you can find a solution to that set of constraints on natural numbers, it actually means that you have bounded the number of times each rejecting state can be reached, right? Because your constraints had made sure that whenever you're reaching a rejecting state, the number that you're getting is greater than the number that you had earlier, right? So for example, if you had a cycle involving a rejecting state, actually a cycle can be taken involving a rejecting state, right? You'll start off with a number here, and then, depending on the next state, whether it is rejecting or not, it has to be either greater than or greater than equal to, greater than equal to, greater than equal to, and finally it again has to be greater. So the number here has to be greater than the number here. That is an unsatisfiable system of constraints. A number cannot be greater than itself. So every time you have a cycle here, you come up with a set of constraints that is unsatisfiable. And the only way to satisfy the system of constraints is when you don't have cycles on the rejecting states. So you basically have a system of constraints now, and you solve that system of constraints, and you basically get a solution. Whether this implementation, right? I mean, what this is giving you is whether this implementation is a correct implementation or not. Right? So this is a way of checking whether a given implementation is a correct implementation or not. What we want to do is we want to check whether there is an implementation which is a correct implementation or not. So we don't have an implementation to build this product graph in the first place. So we basically encode that also symbolically. We say, okay, my implementation can have up to n states. I do not know what the transition structure of my implementation is, but I will say, okay, so basically, let me just write it down. So basically, if I say I have an implementation with n states, I will come up with a system of constraints saying that, okay, for the various possible combinations of inputs and outputs, I'll say, okay, from state 1, so let us say these states are state 1 to state n. So from state 1 on input combination 1, right? Let's say input combination 1. I can go to another state, but I don't know what this state is, but this has to be one of those numbers, right? So I basically write this out for every state. I say, okay, from state 1 on input combination 1, I will have some state which I represent by a variable. On input combination 2, I'll have another state represented by another variable. Third state. Now these states could be the same, they may not be the same. And I say, okay, therefore I will represent my transition system. Actually representing a bounded transition system implicitly is not very difficult. We are just saying that I need a function that will take a state variable, and it will take the values of the inputs and the outputs, and it will give me another natural number. So basically I need a function which goes from natural number, and it will go from the inputs, right? 2 raised to inputs, 2 raised to outputs, and it will go to another natural number. And this natural number is bounded, which is less than or equal to, let us say our bound is some k. So this is less than or equal to k, and this is also less than or equal to k. So I'm looking for a function like this, which goes from 0, 1 to k, combination of inputs, combination of outputs to 0, 1 to k. And this I can encode it as an uninterpreted function on these data types with this as return type. Okay, so I can say this is an uninterpreted function which takes 3 arguments. First is a natural number less than or equal to k. Second is Boolean values of the inputs. The third is Boolean values of the outputs. And it gives me another natural number less than or equal to k. But this function is uninterpreted. I don't know what this function is. Right? So this is basically encoding a symbolic encoding of an arbitrary state machine, of an arbitrary milli machine, which has up to k states. And now I'm going to use this encoding to construct the cross product. Right? So I will say that, okay, from, basically the cross product is, there is a state. So we will say that, so is, let's say that I have a predicate which is cross product state. And this will take a natural number less than or equal to k, which will denote as state of the milli machine. And it will take a state from my universal Kobuki automaton. Right? So this is really from NQ to true false, which says whether there is such a product state or not. Right? Really, whether such a product state is reachable or not. Right? And so for every such thing, I am now going to construct this thing, saying that, okay, if I had such a product state, and if there was a transition which takes me to another product state, and if this was a rejecting thing, then the number here has to be strictly less than the number here. And if I had a product state where this was already rejecting and this was already rejecting where I'm going to, then the number here, if I have a product state where I have an accepting thing, where I have a rejecting state and I'm reaching from another state, then the number here has to be strictly greater than the number here. And if I have a product state where which is a non-rejecting component, then the number here is greater than equal to the number here. So there is a bunch of constraints that I can write down like this. In the interest, oh my goodness, seriously overshot. So in the interest of time, let me just maybe I'll put that up in the slides that I sent just to see that. But I hope you can see that we are basically encoding the unknown implementation having n states using an uninterpreted function. And then we are writing out the same constraints that we saw earlier using this uninterpreted function. So we'll say that, okay, if state 1 can go to state 3 on this input and this output, and if in the universal Kobuki automaton, which I already have, I can go from a certain state Q1 to a certain state Q2 on the same inputs and same outputs, then, depending on whether the state is a rejecting state or not, the number here should be greater than equal to the number here, or the number here should be strictly greater than the number. Okay, and then we finally solve the system of constraints. So let me stop here, and I'm sorry I've not kept track of time, but we will start the second session a bit late. I definitely don't want to deprive you of your break. So basically, these are the two steps: constructing the universal Kobuki automaton, fairly straightforward. Constructing the system of constraints. Once you have an implementation, I showed you it is actually very simple, but we don't have an implementation, so we come up with a symbolic implementation. How is a symbolic implementation represented? By an uninterpreted function. And then we formulate the system of constraints using that uninterpreted function, bound whatever we want to bound there, and then just solve it. Okay. So with that, let me end. I mean, if somebody has a question, it's fine. Otherwise, please go grab your tea, take your break. Shubhajit, I'm really sorry I sort of looked at the time when it was 10:35, but then I lost track of time.
No, I think it's perfectly fine. Actually, I was going to suggest that let's continue this till 11 and then take a break, so that the next section there is a break between this section and the next.
Oh, is it? You want to do it that way?
Yeah, I think this sounds good. I mean, this actually worked out well for me. So,
well, no, I ate into the break time.
No, I think we can take a break now, so that before the next section they have a break, so that there is a time to switch context. So
okay. Yeah, so whatever you decide.
So Supratik, I have one small question. So, like, why is it not, or maybe we are doing that, maybe I'm not seeing it well. But is it not the same as like a lasso detection on the rejection state?
Is it not what?
Like detecting a cycle or a lasso on the rejection state?
No. So if you have the implementation, of course, it's detecting a cycle, but we don't have the implementation. No?
Right,
Yes.
but we have symbolically encoded it. I mean that we now we in some like
Yeah.
symbolically we have the constraint. So
Yeah.
then we are okay.
So it is symbolic cycle detection. Yes.
Acha, okay, I see. Sure.
And the way the symbolic cycle detection is done here is by saying that a number becomes greater than itself.
I see. Sure.
Right. So, I mean, the reason I wanted to sort of first illustrate it with a given implementation is so that it becomes very easy to see that once the implementation is given, I'm just looking for a cycle from a state back to itself. And then I don't even need to put these numbers and all of that. I can just search for a cycle from rejecting state back to itself. But in general, we will not have this implementation, and we're searching for this implementation. So the same problem can be formulated as, you basically associate a number with each cross product state and say some of these are strictly greater, some of these are greater than equal to, and just search for a consistent assignment.
Okay, got it.
And in the symbolic thing, we do exactly that. So in the symbolic thing, we basically, I mean, it looks like the following. We will say that, from, so it will look like the following, that for all I in, let us say, 0 to k or 0 to k minus 1, this is representing the state of the Mealy machine, the symbolic state of the Mealy machine, right? We will say that, and for all q in the set of states of the universal Kobuki automaton, we will say that, so we will, first say that, okay, so is this a cross product state, right? I and q, and really I should say I prime, q prime, right? So if this is a cross product state, and
Oh, I see. Okay, I see the problem. Okay, because even this is not known that whether every such. Okay, so because I was trying to take correspondence with like hardware verification, they are exactly that. This is what we do, right? I mean, we just take a cross product and then try to see if there is a cycle.
But in the hardware verification, you already have a
yes. Now, I sort of missed that. Yeah. So right now we don't even know if something is a product state or not.
Exactly.
Right.
We don't have this, right? I mean, suppose I block this out and I say, yes, you just have a two-state finite state machine. So I don't know.
Right. So have people tried out like enumerative synthesis where they just enumerate these Mealy machines and just check?
Yeah,
like
so
that has been very successful in program synthesis. So I was just wondering
in program synthesis, yeah. So the reason I think that has been successful in program synthesis is because you can severely constrain the enumeration space. You sort of come up with models. There are these model instantiation techniques which allow you to basically come up with promising models, promising instantiations. Here it is not very clear. I do not know if somebody has tried, but this from this universal Kobuki automaton, which is, I mean, if it was a deterministic parity automaton, I would have said, yeah, the implementation is finally really going to look like this, right? But if this is a universal Kobuki automaton, it's a non-deterministic automaton, it is not clear what the final implementation will look like. So, but if there are, I'm not aware, but if there are special cases where we can say that if this is the universal Kobuki automaton, these are the promising candidates for enumerating the implementation, then yes, I mean, we can just enumerate them and check for cycles.
Right.
So yeah, I think maybe in the last part, this part didn't get said properly, that if you have this, then it's just cycle detection.
Exactly.
But our problem is that we don't have this.
So,
Right?
so the main difficulty here is that the product states are not known exactly. What exactly is the? So that's why
Exactly.
we have this additional thing, which is product state, like the predicate that you had there.
Exactly. So I don't have this.
Right.
I just know that there are two states, but I don't
Correct.
know what the transitions are on these two
Right.
states.
Right.
And as I showed at the beginning, I mean, trying to enumerate all possible milli machines on two states or on n states explicitly is explosive. I mean, that
Right.
will explode. So we want to do that enumeration implicitly, symbolically,
Right.
and
Right.
that is what we were doing here. We were saying that okay, for all states, I know that there'll be up to k states. So for all present state and next state, and for all present state and next state, right? As long as there exists kind of input combination, right? So let us say I a subset of inputs, and O a subset of outputs, right? So if this state is there, and if it is the case that this uninterpreted function f with I and O gives you I prime, and in the automaton, in the universal Kobuki automaton, you see that from Q on I comma O, you're going to Q prime in the Kobuki automaton, right? Uh, then then you say that is CP state I prime Q prime is true, right? And you also say that the number that you're associating, let's call it some number lambda, let's say. So lambda of IQ uh, is uh, less than or equal to lambda of I prime Q prime. Yeah, so that will of course depend on whether Q prime is rejecting or not, right? So it
Right.
is this, and if Q prime, if Q prime is rejecting, implies that lambda of I prime Q prime is strictly greater than lambda IQ, right? This is another uninterpreted function, right? And otherwise, Q prime is non-rejecting, implies lambda is greater than equal to, right?
Right. Right. Okay,
And
got it.
this is the system of constraints you solve. So your solution is going to give you valuation, and of course, initially you say that the initial state of the milli machine and the initial state of the automaton is, of course, a CP state, is a cross product state. So this will give you what are the cross product states, right? And it will give you an interpretation of F, and it will also give you an interpretation of lambda,
Right. Right. Right.
right? The interpretation of F is the milli machine that you have synthesized. These are the cross product states that mattered in the cross product graph of that milli machine with the universal cross Kobuki automaton. And because you are able to solve this thing on integers, right? It means that there is no cycle on a rejecting state.
Got it. Got it. Yeah. Sure.
Right? So therefore, you really need to go to, so really, as you can see, that this is a formula in QBF, right? I mean, because everything is bounded here, I can encode everything using propositional logic, and then this is a problem in QBF. And so really, I mean, the latest advances that have happened in bounded synthesis make use of QBF. In fact, they make use of dependency QBF, which you have worked on.
Right.
Right? Because we know, I mean, what these things should be depending on.
Correct. Correct. Correct.
Right? So, so that is the constraint solving that you want to do. But of course, you can blast out everything in terms of propositions, and then list out all of these explicitly. Basically, replace this by conjunctions and replace this by disjunctions and all that.
Yeah, makes sense. Makes a lot of
Go
sense.
it down into a SAT as well. But really, the power of this is when you can use QBF and specifically DQBF.
Correct.
So this is the final constraint, how it looks like, and you feed it to a constraint solver, and it says no. It means there is no implementation with up to k states. I mean, here I used k for the bound on the number of states. You can see that I can write this constraint if you want me to bound the number of cycles or something. I just have to encode it up.
Hmm.
And if it gives you a solution, you just read out F, and that's the state transition table of
The implementation.
the Mealy machine. All right. So okay, we meet at 11:30 then.
Yeah. So let's meet at 11:30.
Right, and we'll start with hardware verification. So yeah, I guess I overshot all kinds of
No, but
civil
it was super
limits.
cool. It was actually awesome. Actually, this, 2
Okay, I
hours
hope-
doing this is too much actually.
Yeah, actually, this topic is so vast, and yeah, I think anyway.
Yeah. So I think
I hope
I'll
something has been conveyed. Uh, I hope the two topics I covered today are actually very practical.
very practical. Absolutely.
What
I
I
mean,
covered
it would have been
yesterday was the theory, and that theory it works if you are lucky, but if you aren't, it may not work. I guess so.
So does Strix take LTL or does it take GR1?
No, Strix takes full LTL.
Full LTL, I see. Oh yeah,
But
you were
it
giving
has
formula which was
amazing. I mean, that paper is really quite dense.
So it's somewhat old, right? It's 14, 15 or somewhere there. The Strix paper.
Yeah, I think their original paper was 14, 15, somewhere around that time. But they have been, uh, and then there was a journal version later. But they have been implementing newer things in Strix. So, for example, even in their web page, they mention that we have stopped supporting something and we are supporting something else now.
Oh, I see.
So, yeah, I think the tool they have been continually working on, but yeah, but that is the winner. That's the best that we have.
And it's a huge improvement. Like last few years, it has been like, I mean, this area has like grown like anything.
Yes, absolutely.
And nowadays, people are even like having these reinforcement learning and reactive synthesis together, and so there's a lot of interest in.
Yeah, absolutely. So, basically, I think this area is just going to explode.
Absolutely.
Yeah, there is, and for this bounded synthesis, there is this tool. I don't know whether there is a web version of this tool, but there's this tool called BOSI.
I see. Okay. Yeah, I've heard about it. I've not used it ever.
Yeah. So, I mean, GitHub and all is there for this, but I don't know whether there is a web version of it. So, the GitHub thing I can show.
Sir?
Yeah.
Sir, I have a question. Like this is a cross product state, right? So for that we will require the Mealy machine. So is it like we have the bookie automaton? Yeah.
For this we require a Mealy machine.
No, so I'm trying to understand. Like suppose we have the automata for the specification, right? Then for that we have the input, and for that we will run the machine and find out what is the next output. Is it like that? How will we check if it is cross product state or not?
Okay, so you can see my screen, right?
Yes.
So the point is, I showed all of the cross product construction just to explain what do we mean by cross product construction.
Yes.
But really, you don't have this thing. You don't have the Mealy machine. This is the Mealy machine you're trying to find out.
Okay.
Right. So you just have this, and you have a bound k, maybe you say 10 states.
Yeah. So let's take that two example. Okay.
Okay, k is 2.
Yeah.
Right. So you say k is 2. So now there can be several different kinds of Mealy machines with 2 states.
Yes.
So you can't construct this, right? I mean,
yes.
You can say, okay, the cross product. I mean, you can't construct these transitions.
Yes.
right? So you can say that, okay, if there are two states, let's call those two states magenta and yellow, or whatever, magenta and orange. But I don't know which state transitions to which
Transitions.
state, right?
Yes. Yes.
So we don't have this. We have, if you say two states, this is all that we have, right?
Yes.
So now, how do I construct this? Because, as I said, eventually we have to look for a cycle in this. So unless I have the edges here, so of course, one can say that there is no edge from A to B. So clearly there will be no edge going between this or between this, right? That's fine. But there is an edge from. So for example, there is an edge from this blue to this red, right?
Yes.
So will I have an edge in the cross product from here to here? Will I have an edge in the cross product from here to here? I don't know. It depends on. So for example, the milli machine that we saw, right?
Yeah.
Was,
There was no edge there.
there was no edge, but here is another milli machine for which there will be an edge, right? So for example,
Yes.
suppose I say that in my machine, if this is y1 and y2, there is a loop like this, let's say in my milli machine. So then indeed from here to here, I can go there on a y1 and y2, right? Because from the magenta, I can go to the magenta on y1 and y2, and from the blue, I can go to the red on y1 and y2. So it depends on what are the transitions in the milli machine, what are the labels. I mean, under what input and output conditions can I undertake those transitions? But that is the unknown part. That's
Okay,
what
so
we
that
don't
we
know.
have to find out. Yes.
Right. So that is what we are saying, that okay, we don't know, but let that be a function. So let that be a function which will take 1 or 2 in this case, let us say, or using the earlier notation 0 or 1. So let's say this is state 0 and this is state 1, right? And it will take a subset of
Inputs.
inputs. So 2 raised to x1 x2 in our case. So these are the inputs that are true, and this will take a subset of the outputs y1 y2, and this will give me something back in 0 1, right?
Yes.
And this is the next state function. So I also want to have I mean yeah, so you
Yes,
can
sir.
say that this is all. So another way to say this is that when this transition to this transition is happening on these inputs, this is also telling you what are the values of the outputs that will get generated.
So
Right?
the SMT solver will give us such f that condition is satisfied.
Yeah. So basically, this is an uninterpreted function. To the SMT solver, we are just saying the type of the function is this. It takes
Yes.
3 arguments. The first is either 0 or 1 natural number. The second is some subset of x1, x2. The third is some subset of y1, y2. And it will give me an output which is 0, 1. But it's an uninterpreted function. I don't know what that is. Because if I knew this, I would know what this milli machine is.
Yeah, then we can just directly find out by checking whether there is a loop or not.
Yeah, so we ask the SMT solver that can you give me an interpretation for this f such that certain things are satisfied. In fact, what is satisfied? That the initial state is certainly a cross product state. And if I have already something as a cross product state, and then I have a transition where I can move both in the automaton and in this, basically f allows me to go there. Right? I don't know what f is, but if f allows me to go, then I'll have that cross product state. And depending on whether I'm reaching a rejecting state or non-rejecting state, the number here has to be greater than the number here, or the number it has to be greater than equal.
Yeah. Yeah. Thank you.
So that's exactly what we
Yes.
Sir, Roger?
Yeah.
So in this page, if q prime is rejecting, that implies lambda I prime, comma q prime greater than the lambda I q, right?
Yes.
So this constraint will be, suppose if you got a cycle, then this will be the unset region, right? Because
exactly. This will contribute to the answer.
So if we get a unset, so the constraint for that will be this guy only. Though, can we get unset from other part of the constraint?
I mean, the other parts of the constraint are also important for. So, for example, let's look at. Oh, I deleted that, I think. Right. I mean, I need to know that, so let us say there is, let's consider a cycle like this, right? And let us say that there are non-rejecting states in between over here. Right? Or actually, let's say I have a cycle between non-rejecting states. This is actually perfectly fine. This doesn't cause any problem. Okay. Now, unless I say that the number here can be greater than equal to the number here, and the number here can be greater than equal to the number here, and the number here can be greater than equal to the number here. Basically, unless I say that all of these have to be equal, I won't find a solution for this. Even if there is one strict inequality here, there is no solution for assigning numbers.
Correct.
Right. So, you do not know what your milli machine is. It may actually give rise to us. I mean, in the example we had, there was a cycle, right, between these two. Now, unless I say that this can be greater than equal to this and this can be greater than equal to this, that unless we put that equality part, we won't be able to satisfy this. So we might get, if I say both of them are greater than, then even this might become unsatisfied. Right? So basically, we want to look at cycles and we want to separate out the good cycles from the bad cycles. Right? The good cycles will allow us to have a solution because I can set everything equal. The bad cycles will not allow us to have a solution because there will be at least one strict inequality. But there might be things shared between the good cycles and the bad cycles, right? I mean, this might be part of another thing here, which might be part of a bad. So this might be part of a bad cycle as well. So when I'm looking at this, I want to get unsatisfiability, but when I'm looking at this, I don't want to get unsatisfied. But of course, this will be constrained to say that the value that you put here has to be strictly less than the value that you put here.
Okay.
All of these values can be the same.
Thank you.
So because we do not know what the structure is a priori, so we basically put the constraints depending on, for example, we do not know what f is going to be, right? So, I mean, this f will give you values for I and O, and that I and O will determine what Q prime is. So we want to put all of these. So I didn't understand. So was that your question, or?
Yeah, it's fine.
The unsatisfiability really comes from the strict inequality. But if you are saying that we can ignore these, no, we cannot, because they also determine values that, as I said, I could have a good cycle, and then from there might be a bad cycle. So I need to know the values here, so that from there I can determine the values here.
Actually, my doubt was is the inequality part is the where we'll get the unsatisfiability, or
the strict inequality part?
Yeah, strict inequality.
Yes, that's the only place where unsatisfiability.
Okay. Thank you.